Hello, chemists. My name is Mr. Gopal. Today we're going to talk about chemical bonding, which is such a crucial part of the Regents Chemistry course. Specifically, I'm going to introduce the topic. And so not only are we going to define chemical bonding, but we're also going to take a look at the two main types of chemical bonding that Regents Chemistry is concerned with, which are the two most important types. If we look here, this is going into something that's been going on since the beginning of the year in chemistry that I just want to talk about on this 8th slide. And that is specifically that you have to get used to particle diagrams, all right? There are various types of particle diagrams. This one is at the microscopic level. We're looking at individual atoms, kind of abstracted. So we see 4 hydrogen atoms surrounding a carbon atom. This is one of the two main types of bonding we're going to talk about later on. But the idea here is that we can see each atom and we have color-coded electrons, specifically valence electrons that belong to hydrogen in red, and valence electrons that belong to carbon in blue. I'm going to review a bunch of terms at the beginning of this, but first I want to look at their introduction and model because I think it's a great place to start. If you've ever made cupcakes or baked anything, then you will have the idea that when these cupcakes or cakes or brownies or whatever it is, when they come out of the oven, they look completely different from when they went in. When they went in, they were a collection of different ingredients. When they come out baked, there's something about the process of convection heat in an oven that is allowing chemical bonds to occur. And we can see that all of these things change completely. And we were no longer able to extract the flour, the sugar, the eggs, or the milk, or whatever else you put in them from the entire thing. The brownie or the cake or the cupcake, whatever it is, it includes a new form of all of that stuff because certain things have bonded with each other. And that brings me to one crucial aspect of noticing chemical bonds in real life. And that is specifically that things are going to usually look completely different post-bonding process than the way that they looked pre-bonding processes. And that's because we're creating new combinations of elements, usually. And so specifically, we have this idea that a chemical bond is like a bond in real life insofar as it's a force of attraction between atoms or ions. So I have a bond with my family, I have a bond with my best friends, and so on and so forth. Different elements at the atomic level will have a bond with each other based on certain characteristics and combinations of them, all right? And so bonds will form specifically at that atomic level when atoms either share or transfer what we call valence electrons. I'm shortly going to jump back into a whiteboard just to go over essential terms, all right? But valence electrons are the electrons in the outer energy level, and they're the ones that are going to be involved in bonding processes. As we know, hopefully from our periodic trends and study of the Bohr model in previous units, we know that most elements will have multiple energy levels with electrons in them. And usually it's the outer shell that is going to be concerning us because that's the shell that has the weakest attraction to the nucleus and therefore is the most susceptible to bonding and either sharing those electrons with other atoms of different elements or transferring them over to other elements. And so understanding why chemical bonds form, it's important to understand that part of it has to do with the patterns that we see on the periodic table. I have here a periodic table that I want to show you first, actually, before we go back to the slide deck. All right, so if I go here, I rotate that, we have here the Regents reference table page for the periodic table of elements. And I want to go back through crucial aspects of this that are essential to bonding. Okay, and these are going to help us distinguish the two types of bonds that we have. All right, there are a few clues on here if you ever forget certain things that are valuable to know about which elements might bond in certain fashions with other elements. So I'm going to take group 1, for example, and I'm going to go specifically to sodium over here. We can see the electron configuration of sodium. What this would mean in the first place is that I'm going to annotate a little bit here. If I had an atom of sodium, let's say that here's my nucleus in red. Inside of that, I'm going to have 11 protons and 11 neutrons. Sorry, change the stylus. 11 protons, 11 neutrons. And then because of this electron configuration that I have here of 2-8-1, that means that my first energy level, I'm going to do these in blue just for contrast. My first energy level is going to have 2 electrons in it. All right, I'm going to pick a different color for that. First, I'm going to make all my levels actually. Undo, sorry. There we go. Let's say that's my second. Let's say here's my third. It's okay. That's actually I'm gonna undo it. I'm gonna make that one more time. Say here's my third. There we go. They're properly spaced. Sorry about that. And I'm gonna use orange to represent electrons just so we can see this accurately. So 2-8-1 means here in my innermost blue circle, which is my first energy level, I'm gonna have 2 electrons here. Okay, I'm making them bigger than they probably would be in a relative diagram in order to help you see them. Now in the next one, I'm gonna have 8. So let me apportion those out. 1, 2, 3, 4, 5, 6, 7, 8. And then in the outer one, I just have this 1. And as we talked about, that outer shell is the one that we're focused on. So that outer shell only has 1, all right? And hopefully you remember this other aspect of that outer shell, that it has a certain electronegativity, which is a tendency to want more electrons, okay? And we know from studying periodic trends also that elements that are towards the left-hand side have a low electronegativity. So let me change this and I'm gonna label this. This is our sodium atom, all right? And now I'm gonna go over here to the other side and I'm gonna take chlorine. And chlorine is gonna be the same as this, all right? Let me see if I can make it quicker than the previous one. Chlorine's gonna have 17 protons and 17 neutrons inside, as we can see from the atomic number here. And then outside of that, we're gonna have 3 shells, the first 2 of which are the same as the first 2 or the inner 2 of sodium. There we go, I'm getting better at that. So I'm gonna have 2 electrons in the innermost energy level. I'm gonna have 8 in the next one. But now I'm gonna have 7, all right, in this outermost one. 2, 3, 4, 5, 6. Here's my 7th. Okay, so this is an atom of chlorine. Sorry, I almost said calcium. Chlorine. So as we can see in our outermost shell of sodium, we have 1 electron. In our outermost shell of chlorine, we have 7 electrons. Chlorine is nearly all the way to the right, so it has a very high electronegativity. It's part of a family called the halogens, and all the elements in the halogen family, group 17, they all really want to finish filling their shells, okay? So they have very high electronegativity. On the other hand, as I said before, sodium's got that lone electron, and it would take so much less energy for it to give it up than for it to try to take in 7 more and complete its shell. This brings me back to the basic principle with bonding and with creating ions from elements, and that is that atoms want to be stable. And what it means to be stable is it means that you have a complete outer shell. And so hopefully you can see that the logical move here, that what both these elements want, they're such a great pair for this, is sodium would happily give up its electron to chlorine, allowing it to drop that outer energy level and just have 2 complete outer energy levels. And meanwhile, chlorine completely fills its outer energy level and now has a configuration of 288. Okay, what I've just demonstrated is the basic bond for table salt, because if we look at both of these, sodium chloride, this bond, is what makes table salt. All right. Other things to note about this bond are that sodium is a metal while chlorine is a nonmetal. All right. And this is going to help us categorize both the bonds and the behavior. Okay. So we talked about an electron transfer. I'm going to talk shortly about that, but an electron transfer is particular to an ionic bond. And an ionic bond is a bond between a metal and a nonmetal. All right. So this fits all the criteria. Sodium's a metal, chlorine's a nonmetal. Sodium transfers 1 electron over. Both of these things are classic characteristics of ionic bonds. And so now you've taken a look at your first type of bond. All right. I'm going to clear this screen. And I'm going to go back to some general comments. Now, the video is getting a little bit too long for me to talk about the other type of bonding in as much depth, but that's okay. First thing that I want to do is I want to go back and I want to look at their example because their example covers this other type. And I'm going to talk about it quickly. And the main thing that I want to talk about here, I'm not going to count up all of the atoms involved, or sorry, all of the electrons, valence electrons involved in the bond between the 2 hydrogen atoms and the 1 oxygen atom. What I am going to talk about is we can see over here that there's an overlap. I'm going to undo that. There's an overlap right here where there is not a transfer being demonstrated of electrons between the hydrogen atom and the oxygen atom, or vice versa. Rather, there's a sharing. So we don't need to go into this back on the periodic table, but oxygen has 6 valence electrons. Hydrogen has 1 in each atom. When hydrogen connects over, it shares 1 of its electrons and it utilizes 1 of oxygen's valence electrons. And so 2 atoms of hydrogen doing that allows oxygen to incorporate 2 more into its outer shell, giving it 8. And each hydrogen atom there takes 1 electron and is sharing that. And so it gets 2. And so through this sharing process, both hydrogen and oxygen have their valence shells or outer shells completed. Now, this is an example of the second type of bonding, which is called covalent bonding. Other things to mention in the slide deck. This video essentially covers the same process, but what I wanted to add in is that you really should look to the information that you've already learned about patterns in the periodic table and how to read that periodic table in order to predict what types of bonds there will be. Now, there's a third type that you're not looking at in this particular lesson called metallic bonds between more than one metal, but that's of less of a concern in Regents Chemistry. You do need to know about it, but you don't spend nearly as much time studying it because so many of the bonds that you want to look at in depth are either covalent or ionic. So how can we remember? Well, we can categorize the elements in the bonds. Are they metals or nonmetals? then we can also look at these oxidation states. And that's where I'm going to pick up next time. These oxidation states give the usual tendencies of an element in a bonding situation. So for example, oxygen would take on 2 more electrons, changing its overall charge from 0 to -2. All right. Sodium would gladly give up 1 electron, changing its overall charge to +1. And chlorine would ideally take in 1, changing its overall charge to -1. Finally, hydrogen would gladly kind of share 1 or maybe give 1 up. And if it gave 1 up, it would change its overall charge to +1. Okay, so there's a connection between the types of elements and the types of bonds formed, also between the electronegativity and the amount of valence electrons, and therefore the tendency of a particular element in a bond. So this has been a lesson where I tried to assimilate visually a lot of the characteristics of bonding. It's okay if you don't understand this completely right away, because you will spend a lot of time looking at particular bonds to practice. And I can think of no better way to get more comfortable. You're going to look at various bonds and try to categorize them in class, but keep those things in mind. Is it a metal or a non-metal? Is the other one a metal or a non-metal? Therefore, should it be an ionic, which is metal and non-metal, or a covalent, which is non-metal and non-metal? And therefore, if it's ionic, should it not be transferring electrons? And so from which element is it transferring from and to? And on the other hand, if it's a covalent bond, okay, it's sharing. I need to figure out the configuration if I were to draw that. And we will pick up with that in the following video, which will be a lesson on trying to figure out how to represent these visually in the correct way, depending on the type of bond. I hope this has been instructive and helped you make some of these concepts a little bit more concrete, and I will see you next time.